Hi everyone, here is our group's presentation. Our group's topic is time series motifs detection. We are group 10. Here is our group members. My name is Xie Chong Shan. Our presentation is divided into 6 parts. In the first part, I will give a brief introduction about our topic. Let me first introduce the basic knowledge about time series motifs first. Time series motifs are repeated patterns found within the time series. Motif findings are useful for exploratory data mining. For many data mining tasks, the detection of such repeated patterns is important. It has been used as an important subroutine in many time series data mining tasks and applications, such as association rule mining, data visualization, classification, clustering, anomaly detection, and behavior recognition. If we can extract useful information from data and series data automatically, it will contribute to the whole industry. Here is a few examples. The figure in the left-hand side is describing a laundry motif in an electronic power demand dataset. It consists of a highly conserved prefix and suffix. It can be used in many quotidian human behavior, such as handshake, basketball game free show, given the acceleration sensor data. It can also be used in animal behavior detection, such as insect ingestion behavior as well. Due to its diverse applications in many different domains, proposing a fast and universal algorithm is compromising. In our project, we try to propose some improvements to the algorithm from the original paper. Then we try to find the semantic motifs with higher efficiency. Here is our main work in our project. First, we re-explain the motifs finding algorithm in the original paper. Then try to make some improvements on the motifs finding algorithm. After that, we are doing our experiment. We implement the original method first and then make improvements by the following ways. The first one is using different distance matrices. We use Manhattan distance instead of Euclidean distance. The second one is finding motifs in two sequence. The third one is adapting algorithm to find more complicated patterns.
Hello everyone, this is Huang Louis speaking. In recent years, there has been a surge of interest in time series topics. Some ideas are proposed such as replacing the including distance with dynamic time wrapping, length inferent including distance, or other epinomes. For more details in application, Simple, which is proposed to solve music information retrieval task using subsequence joins, Shima proposed a natural language search mechanism for searching most similar time series. And someone invented a new distance measure method called MPDist, which can be more efficient when handling some datasets with missing values or spurious regions. But the problem is that they just improve the scalability in search motifs, so that is why we try to expand the expressiveness of definition of motif. We may consider the dynamic time wrapping (DWT) a very useful method in many time series data mining tasks, but it is hard to map different change numbers in similar sequences. For example, DWT is able to make up for tiny local misalignments. In the given situation, DTW is not able to map 4 peaks to 6 peaks. Before describing our algorithm, we give definitions of the key terms used in this paper. A time series T of length n is a sequence of real-valued numbers. As an expansion of program domain, we can also deal with strings, so we may also use a string definition and let T of length n be a sequence of characters, such as CI, T equals C1, C2, and Cn. A continuous ordered subset of a sequence is called subsequence. The definition as follows. The first subscript is the starting index, and the second subscript is the length of its continuous subset. The most similar subsequence pair of a time series is time series motif. In this definition, dist is a function that measures the distance between the subsequence. A distance profile of a time series is a factor that contains the distance between a given subsequence T and all other subsequences with length m. In semantic motif, something is the semantic motif pair if and only if in the following situation. Same idea as definition 4, we can use the semantic pair distance for each semantic motif pair to form a semantic matrix profile. A semantic matrix profile is a meta-time series SMP. Each element represents the similarity between each semantic motif and its nearest neighbor.
My name is Liu Yingjie. Let me demonstrate how the original algorithm in the paper works. We want to find a pair of motifs containing a prefix, a suffix, and a don't care region in the middle, which may have different lengths. We construct the solution step by step from the simplest scenario. Suppose we just find two simple subsequences of length s that have the minimal distance between them. We can build a distance matrix D based on our distance profile definition. Then simply find the minimum element in D, and its indexes are the starting positions of the two corresponding subsequences. Then we consider adding the notation of prefix and suffix. Suppose their lengths are both s. Remember that we already have matrix D, so we can directly reuse in this formula. Finally, we consider adding back the don't care region. This time, instead of adding a value from a predefined offset such as this, for each pair of ing, we add the minimal value from the orange box in this picture. It can be easily proved by definition that this formula can give us what we want. This method sounds very simple, but if we do it in the simple naive way, we may have some redundant computation. Whenever we move j to j plus 1, if we recreate the offset matrix and find the minimum, we are doing redundant computation on the middle rows. This can have a huge performance impact, and we want to avoid it. Now I will illustrate the method to compress each column beforehand. The naive method takes min on k and l at the same time, but we can separate them. We build m and n matrices by these formulas. Note that this is just a simple by definition decomposition of computing steps. Then we can use the n matrix to replace this matrix. Now our problem is simplified to be just like the previous one. We can only add d and n and we get the result. Finally, I will address the issue of different prefix and suffix lengths. Suppose the length of prefix is p and the length of suffix is s. If we revisit the last formula on the last page, we know that the first part deals with the prefix and the second part deals with the suffix. With this knowledge, solving this problem is actually pretty easy. At the beginning, we built two matrices dp and ds. These are just our simple distance matrices, but this one is of length p and this one is of length s. Then we build the mn matrices using only ds because m and n only deal with the suffix. However, we need to change this static offset factor from s to p because now the prefix is p. After we have the n matrix, we can add it to matrix dp, the prefix. Then we can find the minimal value in the result matrix, and the corresponding ig positions are the starting positions of the two motifs. As a final note, when we do these calculations, we must always be aware of index boundary issues. I will not go through the exact detail, but of course we have solved them in our code.
I'm He Feifan. The implementation of the algorithm provided by the original paper is based on MATLAB. And in our experiment, we choose to reproduce the algorithms through Python and use number to speed up the algorithm. Initially, we want to use native Python list and loops to find motifs in the numerical list of length 5,000. This takes 80 minutes. Then we use numbar and numpy to rewrite the code, and it just takes 2 minutes to find the same motifs. It is like 45 times speed up. In addition to implementing the method of finding semantic motifs in the waveform data mentioned in the original paper, we also provide a method for searching the prefix and suffix pairs for inputs in the form of a string. When using string form as input, we use added distance to replace the Euclidean distance. For numerical waveform data, we use the following example to illustrate the effect of this algorithm. The data was recorded by an accelerometer from a student's phone, containing acceleration data of her personal activities. The two sequences in the red box recorded the activity of using the elevator. We can regard each red box area as a semantic motif. The bump of the waveform representing the acceleration of the rising and the valley representing the stopping process of elevator. Also, there is a relative flat region between the bump and the valley. The flat region stands for uniform activities of the elevator. During this region, the accelerometer will not receive any acceleration. The more flows rise, the longer the flat area in the middle. The figure shows the result of using our implemented algorithm to find the prefix and the suffix for each elevator activities. Although the first semantic motif has longer don't care area in the middle, our algorithm actually accurately captures the two ups and downs. The right side picture shows the application scenario of searching motifs in disordered strings. The algorithm can also be well applied and finding the target quickly and accurately. We also adopted the algorithm to find prefix and suffix with different lengths. You can see the result here. The red part represents the seal swimming at a constant speed in the sea, and then it found a prey, suddenly accelerated and caught the prey. The yellow part represents that the seal floated to the surface with its prey and swallowed the prey.
Hello, this is Zheng Yang.
So in the last section, we use Euclidean distance in the semantic motif finder algorithm. Now we try to compare different distance measurements method. The first figure is a result of the Euclidean method for finding motif in male Australian firm seal behavior. The second is the result of using cubic term distance method. And the last one is using Manhattan distance. We said that there is a slight incorrect term at the tail of suffix, and this is the original method. Then we look at the cubic term method. The second, the end of the first suffix overlapped with the second prefix. This result is worse than the result of Euclidean distance measurement, which shows that the higher order term may increase the impact of the distance of a single location. Then we tried the Manhattan distance. It is obvious that using Manhattan distance results in a more accurate result because there is not much deviation at the tail anymore. However, in real life, we do not always have a complete time series. We may be affected by various external or internal factors, resulting in a complete or segmented series. Therefore, we continue to improve on the original method of the paper. Similarly, the data we use here is still the behavior data of seals. The first figure is the original picture for two signals of seals. Obviously, there is a high similarity between the beginning of the first sequence and the end of second sequence. So it is possible to find the prefix and the suffix. Then the second figure is a result for Euclidean distance method, which shows the motif defined by prefix and suffix was found accurately. And then for Manhattan distance, we have confirmed its practicality, but there is no obvious performance boost in this example. It can be said that it has almost the same effect as Euclidean distance. However, we know that the computation cost of Manhattan distance is slightly lower than the Euclidean distance, which can be a reason to choose it.
Hello everyone, I'm Liu Donghua and I will continue to introduce the improvement part and the corresponding experiment for our project. Up to now, we only discussed about the semantic motifs that have similar prefix and suffix. What if we want to find a kind of semantic motif consisting of 3 parts? That is a prefix, infix, and suffix. By definition, our goal is to find the ij pair to minimize this function. Obviously, searching in this vast space significantly raises the time complexity. Therefore, we propose a feasible way to simplify this problem by using the previous algorithm we have introduced. Recall that we use the summation of matrix N and matrix D to determine the distance of 2 full candidate 2-part motifs. Let's call the summation matrix ND. We now treat the combination of the original infix and suffix as a new suffix, while the original prefix is still the prefix. Although there can be a don't care region between the original infix and suffix. For the sake of computation, we view the length of the new suffix as n plus s. We can now view ND as the distance matrix of the new suffix and go through the process of the algorithm again to attach it to the original prefix. Then I will choose an example to illustrate the performance of this improvement. The data is from a recording clip of reading famous poetry, The Raven. Actually, if you have ever read this poetry, you will find out that there are a lot of higher frequency phrases. We use both the original algorithm and our 3-part algorithm to find some motif pairs from the audio data and observe the difference. From this figure, we can see that compared with the original algorithm, our improved algorithm finds out an additional suffix which is marked in yellow. The original audio is about 8 minutes. You can see the detailed waveform of the motif we found in the following picture. And when we pay attention to the text at the corresponding position in the original poetry, we find that the prefix and the infix we found correspond to a phrase called "and nothing more." But the suffix corresponds to the beginning of the next sentence. Although they come from different sentences, we still observe the same pronunciation or even the same word in the corresponding position as is shown in the text box. Also, you can check the corresponding part of the audio file.
Darkness there, and nothing more. Deep into this darkness peering, long merely this, and nothing more. Back into the chamber turning.
So our algorithm indeed find out similar motif pairs. And that's all for our presentation. Thanks for your listening.